Hello and welcome to the module on backpropagation, or how we are going to train artificial neural networks and determine the weights. So, to keep things simple, let us start off with a single neuron, right, that is going to have a logistic sigmoid as the output function. So, here, so you are going to write your f hat of x is equal to b plus w transpose x, right, and then you pass that through your sigmoid function O. Right. So, O in this case would be the logistic sigmoid, where we will say O of v is 1 by 1 plus e power minus v. So, we saw this in the last module. So, the error measure that we will be using is a squared error. So, the expected error of the parameters w going to be half times the expected error w is going to be summation I equal 1 to n, where n is the number of training data points that you have, okay, of the squared error for each training data point. So, the way we are going to use this for changing the weights is essentially to compute the gradient of the error. So, essentially that will be the error times the derivative of the output function times minus x I. This is essentially taking the derivative of this with respect to the w function. Once you have computed the gradient of the error with respect to the weights, and then we essentially just change the weights in the direction opposite to the eta times the gradient of these weights, where eta is the essentially the step size parameter. So, this works fine when you have a single neuron, right. So, what about the case when you have layered networks like this, right. So, this is our standard 3 layer neural network, right. So, the first layer is essentially just the inputs, right. So, the second layer of neurons takes in the inputs and computes the output, okay, and these are called the hidden neurons as we discussed in the last module, and then the output layers finally take the output from the hidden units, again do the appropriate transformation and give you the final outputs. Right. So, here, so we will denote the hidden layer outputs by h, and h is given as g of the weighted summation of the inputs, right, and let me introduce a temporary variable here called t, which essentially is the summation of the outputs of the hidden units, and f is finally the transformation O of the outputs of the hidden units, right. So, one thing to note here is that, so I have used different functions g and O for the hidden layer and the output layer, and typically for 2 class classification problems, both g and O are logistic sigmoids, right, as we saw earlier. So, g as well as O would be of the same form 1 by 1 plus e power v, but then if you are having a regression problem, you can essentially use the same setup that we have here, except that O would be linear for the regression problems. So, in which case O would be essentially just passing on the inputs that it is getting, right. So, suppose I have these multiple layers, how would I go about finding the weights of this standard 3 layer outputs, right. So, in some sense finding a training rule for W2 is not very hard, right. So, W2, if you think about it, is just like a single neuron network. So, I can just take all the weights that come to F1, right, and then essentially use the same rule that I used earlier here for a single neuron. I can use the same rule for training F1, except that instead of xi I will be using the output h, right. So, that is clear, right. So, for finding W2 I really can just stick with what I did earlier, right. So, I am going to write that here again just for clarity's sake. So, I have rewritten this in an appropriate fashion for working with this multi-layer networks, right. So, I am going to look at the gradient of the error with respect to a single weight, okay, that runs from the mth neuron here, right, to the kth output neuron, right. This weight runs from the mth hidden neuron to the kth output neuron. Okay, so, this is essentially the kth output, right, minus the prediction given by the neural network. So, that is essentially our error times the derivative of the output function of the kth neuron with respect to the input that it receives times the input that is coming on the mth line, which will be essentially HMI, right. So, if you think about it, that is exactly the update that we had here, except that I have changed the notation to apply to the the second layer weights in the 3 layer network. Okay. So, now the interesting part, so this is fine. So, this we can just get from the single neuron update. So, what do we do about the first layer weights, right. So, let us see how we will do this. This essentially uses the very simple idea of chain rule from differentiation, right. I am going to take a very specific weight here. So, I would like to find the derivative of the error with respect to the first layer weight that runs from the lth input neuron to the mth hidden neuron, okay, right. So, it runs from some lth neuron to the mth neuron. So, we are just looking at this one weight here. We are trying to find out what is the gradient of the error at the output with respect to that one weight. So, I can rewrite this as follows, right. So, the derivative of the error with respect to the first layer weight is essentially the derivative of the error with respect to the output of the mth neuron times the derivative of the mth neuron with respect to the weight, right. So, this makes sense because the weight from the weight to the mth neuron affects the output only via the output of the mth neuron, right. So, it affects the overall output of the network only via the output of the mth neuron. So, I can essentially apply the chain rule here, right. So, let us take this bit by bit. So, if I look at this, right. So, you can see that this is immediately obvious because this is the function we are talking about here. So, if we take the derivative of this with respect to any specific w here, so we will essentially get. So, if we take the derivative of HMI with respect to WML, we are essentially going to get the derivative of G times, okay, the derivative of this expression with respect to WML, which will just be XLI, right. So, this is the second term in the derivative, right. So, the first term in this derivative is the one that requires a little bit more work. So, let us see how we do that, right. So, I am going to try and evaluate that expression here. So, if you think about it, so the different ways in which the output of the mth neuron, right, can influence the overall error is essentially through each one of the output neuron that mth hidden neuron connects to. So, it can influence the error through this output or it can influence the error through this output, right. So, we are essentially summing over all possible outputs k, right, of the error of the gradient of the error with respect to fk and the gradient of fk with respect to the output of the hidden neuron, right. So, we can easily evaluate the derivative. So, the error the derivative of the error with respect to f k. So, if you think about it, so this is the expression we have. So, the derivative of the error with respect to f k right. So, going from this expression, the derivative of the error with respect to f k is going to be, so the negative of y I minus f hat k x I, because we are taking the derivative with respect to f k here. So, we do not have to worry about the further terms that constitute f k. Okay. As far as the second term is concerned, that is essentially looking at this. So, derivative of f k with respect to h m is essentially the derivative of O with respect to h times the derivative of the argument of O with respect to h, which gives us just the weight w k m, complex expression for this. So, before I put these things together, to make things a little simple, let me introduce a small notational thing, so that it makes life a little easier for us. So, I am going to say delta and I am going to say delta k for the input I is essentially the error term times the derivative of the last layer's output function, right. And I also define this term rho m for the input I as the essentially the derivative of g with respect to w times the summation of w k m into delta k of I. Okay. So, putting these together, now we can write our expressions more compactly. Essentially, we can say that dou right. So, the error of the the derivative of the error with respect to the output layer weights, right, with respect to the W2 weights is essentially delta k I times h m I. Likewise, right. So, likewise the derivative of the error with respect to the first layer weights, the weights from the input layer to the hidden layer, is given by rho m I, right, times x L I, right. So, if you think about it, so this part corresponds to this, right, and that comes from here, and x L I is what is left out here, right. So, these expressions look pretty compact, and now we essentially have, so we essentially update the parameters by W k m is just changed by this the gradient here, and W m L is again changed by the gradient that we have computed here. So, one thing I want to point out here, that if your function g or your function O, right, happens to be a sigmoid, okay, right, then g dash is equal to essentially g dash of v is equal to essentially g of v into 1 minus g of v, right. And suppose you are using a tan h function, because you want your outputs to run from -1 to +1, right. Suppose then G dash right, it is 1 minus G V squared, right. Essentially this gives you the, so you can see that the sigmoid functions have a very convenient form for the derivatives, right. So one thing that we have to be careful about here is the fact that these are gradient following methods, and therefore there is a good chance that they will get stuck in local optima, and there are many techniques for getting out of these local optima, but we will not discuss too many of them. The one of the simplest one is of course to try this with multiple starting states, starting points for your weights, and taking the set of weights that gives you the best possible result at the end of some kind of experimentation. Okay. So that brings us to the end of this module on training your neural network using back propagation. So, but this form of training has its own drawbacks. We will see about that in the next module.